Today's new images of 3I Atlas quietly change the conversation again. Not with a dramatic flare or a sudden breakup, but with something more revealing: consistency. What we're looking at now comes from two parallel views of the same moment in time: a high-contrast contour analysis and the raw observational frame. Same object, same exposure window, two very different ways of interrogating the data, and both point to the same conclusion. There's a persistent structure facing the sun. Stay with me until the very end if you want to see what happens next. Additionally, if you're already interested in this, you may like, subscribe, or enable notifications at any moment. Go full screen for the greatest experience, and let's go over the recent changes. That alone is worth slowing down for, because at this stage of an outbound trajectory, we normally expect activity to become more diffuse, less organized, and increasingly dominated by material being swept away from the sun. Instead, the structure here isn't subtle. The contour work pulls it out clearly, and the raw image confirms it's not an artifact of processing. This matters because when a feature survives multiple independent analysis methods, it stops being a hypothesis and becomes a measured property of the object. Let's stay with this image and break down what it's actually telling us. On the left is the contour-enhanced view. Contours don't invent structure. They trace gradients that already exist in the data. Each closed line marks a real change in brightness. What immediately stands out is that these contours are not circular. They're stretched, asymmetric, and biased forward toward the sun. That tells us the inner coma is not expanding evenly in all directions. The strongest brightness gradient is clearly sunward. Now compare that to the raw frame on the right. No contour mat, no edge detection, just photons collected against a background of stars. The same forward-facing structure is still there. Fainter, yes, but aligned in the same direction and anchored to the same position relative to the nucleus. When two very different representations agree on geometry, the probability of noise, tracking error, or overprocessing drops sharply. What this points to is activity confined to specific regions on the nucleus. Instead of a smooth, isotropic outflow, material is being released preferentially along certain directions. That is consistent with jets, not jets inferred only through orbital modeling, but jets visible directly in the morphology of the coma itself. And timing matters here. This image was taken after perihelion, when many comets begin to lose organized structure as their activity weakens. Instead of dissolving into a diffuse cloud, 3I Atlas is still showing coherence in the inner coma. That doesn't tell us yet what's driving it. Ice composition, thermal stress, rotation state, and surface geometry can all play roles. But it does tell us that this object is not simply relaxing into a quiet, fading state. To see whether the structure holds up, we move to independent observations. The next image comes from Mario Ferraco, captured on December 19th during the perigee window, when 3I Atlas was moving at extreme apparent speed across the sky. At wide scale, the object appears as a compact source sliding cleanly through a field of streaked stars. That's important. The stars smear because the telescope is tracking the comet. The comet itself remains sharp. That confirms accurate tracking. Now, look at the process frame. With the background suppressed and the signal enhanced, the same pattern emerges again. A tight central core, a surrounding envelope, and faint but directionally consistent structure extending from the nucleus. This is not random grain. If it were noise, it would rotate, distort, or disappear between frames. Instead, it stays locked to the object. That lock-in is the key point. The brightness plots associated with these frames reinforce the same story. Instead of collapsing rapidly, the activity curve holds and then declines gradually. That behavior is consistent with sustained emission, not a single impulsive event. And the orbital geometry matters here. At the time of these observations, 3I Atlas was still more than 2 astronomical units from the sun, yet showing structured activity we usually associate with much closer distances. Frame by frame, the motion is fast, almost startling, but the internal structure remains coherent. The coma doesn't tear apart. The core doesn't smear. That rules out tracking artifacts. It rules out processing tricks. What remains is intrinsic activity. Now let's step down in resolution. These next images come from Contextual using a C-Star S50, captured minutes apart on the same night. At first glance, the frames look subtle. That's exactly why they matter. There's no heavy processing here, no aggressive filtering. Just longer integration revealing what's actually present. In the 4-minute frame, the object appears compact but slightly asymmetric. By 9 minutes, that asymmetry becomes clearer. The brightness peak is offset. The surrounding glow isn't evenly distributed. Random noise averages out with time. Real structure does not. The elongation here lines up with the same general axis identified in higher resolution datasets. Different observer, different instrument, different processing philosophy, same geometry. This isn't a dramatic jet image. It's something more important. Independent confirmation that 3I Atlas is not behaving like a simple diffuse point source. Even at low resolution, it refuses to smear into symmetry. The coma remains directionally biased, which tells us whatever is shaping it is persistent, not transient. That brings us to the broader context. The next visualization from Stephen Burns shows the positional geometry of 3I Atlas on December 27th. This isn't about brightness. It's about alignment. At that time, the object sits roughly 40 degrees off the sun line, positioned westward in solar coordinates, and riding almost exactly along the ecliptic plane, slightly south. That alone isn't extraordinary. But what matters is what else occupies that geometry at the same time. A rapidly evolving sunspot group appears near the same plane, compact and complex. According to the timeline, its sudden growth begins during this alignment window. To be clear, there is no known physical mechanism linking a distant interstellar object to solar surface activity. Correlation is not causation, but science does pay attention to repeated coincidences in space and time, especially when geometry and timing line up cleanly. What we have now is a convergence of facts, not conclusions. Persistent sunward structure near the nucleus. Independent confirmation across instruments. Coherent morphology despite rapid motion. A precise spatial context within the Sun-Earth system. None of this proves anything extraordinary, but it does narrow the range of explanations. It allows us to rule out simple noise, simple symmetry, and simple fading behavior. And then there's one more reminder of scale. A confirmed lunar impact flash was detected by Armagh Observatory and Planetarium. A brief, sharp burst of light on the moon, exactly what you expect from a high-velocity meteoroid impact. Events like this happen more often than we realize. We simply don't catch them often, and even more rarely with independent confirmation. It's a reminder that space isn't static. It's active, dynamic, interacting constantly with Earth's neighborhood. From interstellar visitors like 3I Atlas to impacts happening right now on the moon, we're observing a system in motion. So the real question isn't whether 3I Atlas is extraordinary. The question is whether we're finally seeing it clearly enough to understand what kind of ordinary it belongs to. Are we simply getting better at detecting structure, or are we witnessing an object whose behavior genuinely falls outside the categories we built from local experience? More data is coming, and each new image doesn't shout answers. It quietly removes excuses. And that's how real mysteries begin to take shape.